Hello, welcome to another video on the brand new, hopefully new, brand new rebranded YAS channel. And today we're going to go back to the basics, laying the foundations with command-based programming. This is, of course, before we get into this tutorial, I want to specify some resources that will help you understand these concepts a lot better. The first thing I want to discuss is going to be reading the documentation from WIPLib here. Of course, if reading documentation isn't suited for you, you can also look at some other helpful resources. For me, that was YouTube videos like this one, like FRC 0 to Autonomous command-based video, or some other. I know teams like this team here has pretty useful information that you can get. Oh, I hate this. Although I would still recommend reading the documentation, as that is literally created by or run by first. Everything you need to know related to that is going to be in WIPLib docs. And then you can also subscribe to the channel. That's a great way to get more resources. And then big emphasis on learning the basics of Java on your own. Once you have a solid foundation on methods and constructors, these concepts that I'm going to be using throughout all my tutorials, you're going to have a lot easier time programming your robot. So let's get started. What is command-based programming? Shamelessly stolen by WIPLibs. What is it? Command-based programming is basically a method of organizing your robot. It's clean, it's modular, and you're able to reuse it, right? Once you write your swerve code, you can use that swerve code for many years to come, or at least with minimal adjustments to it, as well. Everything is in fact modular. You have like code for specific segments of the robot, like your arm, your elevators, and we call that subsystems. And another big part of that is going to be commands. So the robot's behavior is broken down into two main parts, subsystems and commands, and this helps make writing complex robot actions a lot simpler, and we can basically focus on more advanced things rather than trying to squint and look at lines and lines of code, although that's still going to be a part of programming. That's just programming. Subsystems. What is a subsystem, you might be asking? Well, subsystems, they are basically units. They're different mechanisms on the robot. You have, let's say, a robot here. You have an elevator, maybe you have a little arm, and you have a claw on it, and a drivetrain. Those all can be separated into its own subsystem, right? We have the drivetrain here, and so all motors, all sensors, anything that needs to be configured, that's all going to be in one subsystem class. And then we maybe have another subsystem. We call that our elevator subsystem. Oh man, I don't like this. We have our elevator subsystem that's going to have all the sensors, all the things, and tell the robot how to operate it, right? That really is the important thing about a subsystem. It defines that mechanism. It defines how many motors, how many sensors, and it tells the robot, or it tells the code how to make it work. Of course, now that you are able to function and, do things, how to sense stuff, you gotta have commands. And commands are the instructions that actually do it. So think about subsystems as you're creating the robot, creating that mechanism. And then commands, they basically tell the robot how to use that subsystem to accomplish a task that the robot has to perform. if you're going to look at other teams, for example, you're going to notice that teams organize things a little differently. I know some teams have their commands in a separate folder. We at BrownBots put our commands that relate to a subsystem into its own subsystem class, or it's going to be inside the subsystem. So we all have our elevator commands that are in the subsystem, and then our commands for like a swerve, they would be in its own subsystem. But first, talk to your team, see how they run. If you're a rookie team, I recommend just going with what seems the cleanest. Having good foundation is always a great way to start. Of course, even though these teams have many differences, parts of the commands will always be the same. A command has 4 stages: initialization, execution, and then end. And then you have this is function here, is finished. That's going to be always checking to see if you reach your goal. And the last thing you got to know is groups of the command. They're called command composition, and you can use multiple of these commands and combine them into one command, and that would help you accomplish more complex tasks. So what makes up a command? Well, examples of command would be our like drive forward, or launch minibot, maybe grab game piece, instructions, something you would actually tell someone what to do, they would make it do it. And that when you call it, it's going to be sent to our scheduler, which there could be multiple commands on the scheduler. Maybe you have your drive, or you have command 1 that's on your scheduler, and then command 2 on your scheduler, and they're all in this like big queue, and the robot would execute them one by one, right? So how this works is basically it will first initialize it, and then it's going to execute the command, do whatever that command is, and then once it checks and sees that it is finished with the command, it will end this command. And once that command ends, what's going to do is going to remove itself from the scheduler, and then the next command is going to run. One thing I would like to really emphasize is that commands must stop, right? Because you have this big, oh, I do not like that. We have this big, technical difficulties. Okay, we have this queue of commands that are just waiting in line, and if you have this command here, and he is never ever finishing his task, he's always continually doing that, he's never going to leave this line and let all these commands here go after him. And that's why commands must stop. You gotta tell a command when it's gonna finish, and then or else it's just going to run forever. And you got to be really specific about it, right? So let's say, for example, you have a command that's called set height, and it moves your elevator up to that height. And it might seem like that elevator reached its goal. However, you never actually specified that it did. So not only do you have to say, hey, move to this height, you have to say, once you reach that height, you have to cancel the command and leave the scheduler and let the command fall after you follow. So how does this look like? I have an example here of a pretty basic command. It's a set angle command. I have my return type, which is a command. If you don't know how methods work, you have to specify the return type, and then that returns the exact same thing. So I have a command here, and then I have the name of it, which is called set arm angle, and then we have our parameter. So we're going to input degrees into this. And then in here, we're going to return another command. So this command is called set goal. If you want to, let's say, instead of returning another command, you want to run a void method or something else in here, you can do a run and then parentheses again, dash, and then arrow, and then you put your command in here. And what that's going to do, it's going to turn whatever you have inside of these two parentheses into a command. So this is great for maybe put a void method. A void method just has no return. It just does something. So maybe, let's see, what's a good example? Maybe you're checking a height. You want to run that as a command. So you have like check height, and then that's going to run as a command. So that can be useful. And then after here, we have our end statement. This is really important as it lets this command know that, hey, once I reach my goal around this degree, I will cancel this command. It's over. Now I'm going to talk about command compositions. Once again, famously stolen by WIPLib. WPILib, yeah. Command compositions is basically what you call groups of commands. And more important, how my team uses it, or yeah, it's basically how you have to use it, is that it's how you group a bunch of commands from different subsystems together. For example, let's say I want to run my arm, my elevator, and my drivetrain all at the exact same time to score a game piece. I would need to use command composition in order to basically automate this whole process and not just have to individually tell every instruction what to do. I can maybe even put in a method and call this score game piece. There's different methods you can use to control your commands. For example, we have dot repeatedly. And dot repeatedly, it's not really used for having multiple commands, but I put this as an honorable mention because it runs a command over and over again. Let's say you don't want a command to end, right? Let's say you want to hold the current height of the elevator forever. You can basically use a dot repeatedly. And then maybe you have a trigger for it when to start, but dot repeatedly. The next one I want to talk about is going to be and thens. And thens is very, it sounds like what it is. Once this command ends, run, and then run the next command. This is very similar to before starting. So before starting this command here, I want to run this command first, and then I run that one. So there's different use cases. Over here, all these commands here, I would categorize these as parallel commands. Parallel commands basically allow you to run instructions all at the same time, multiple instructions for the same time. So let's have, if we use the example from before that your elevator, your arm, and your drivetrain, you all want to do that efficiently all at the same time, you can use these methods. First thing I want to talk about is along with. So you have one command here, and then along with, so once this command runs, it's going to, along with these methods, so these commands are also going to run with this. And you can put as many commands as you want. You can put one command in here, you can put 3 commands in here, as long as it's just within the 2 quantities. This is very similar to parallel command groups. Parallel command groups are basically multiple commands, and they all run at the same time, and they finish all at the same time. So think this is like a big command. It's a bigger command. You have to, if you want it to end, all of these have to end. A parallel race group is similar to that, as all these commands will run at the same time, but as soon as the fastest one finishes, the rest of the commands are going to end. Last one I want to talk about is parallel deadline. Deadline basically declares this first command here as its deadline group. So parallel, and it's basically saying, hey, once this command here finishes, cancel all the rest of the commands, right? So this command here could be the fastest command. This command could be the second fastest, the slowest, but it only ends as this whole group will only end once this singular command ends. And I visualized it out here for you because that's a lot. This concept took me a really long time to understand. We have our sequential command group right here. And this is your typical one after the other, drive forward, lift the elevator, and then score the game piece. This is, of course, very inefficient as you have to wait for one command after the other, which is why you use a parallel command group. Parallel command groups, you can see here, this command finished, and then this command finished. And once all three of those commands finish, this whole group is able to declare itself finished. This differs from a parallel race group, as if you notice, the gray one, this gray command was able to finish first, which leaves the whole command, which stops the whole command there. So anything here, anything past that, anything slower than that, just cancel the command. This can be like, for example, maybe you're lifting your elevator while driving, and you're driving, you drive to your set point first. You can be midway through lifting up your elevator, and that wouldn't matter. The command would just cancel. And then the last one I'll talk about is parallel deadline group. This declares this green one here as its deadline. So any command past that is gonna basically cancel. And then this one was able to finish because it was able to beat the deadline. Right, this is like scoring, you turning in your assignment, there's a due date, you can't turn it in past that, but you can turn it in before that. Something also useful to know about in command-based programming is going to be triggers. Triggers are, well, they trigger stuff. This is like an event, this is a true or false, and they're helpful as they can basically, they can help indicate when you want to run an instruction. For example, maybe when you would press a button, you press a button, you want something to run, or maybe you sense that you're holding an object. So, hey, when I grab this game piece, run the drive to score command. We can have it so maybe when it's reaching a goal, when I set this height, end the command. And there's a lot more examples of that. You can make it's up to your creativity. And then if you want to learn how to make them, reference the docs. It's a great article. I read through it. It was my first documentation page I ever read. And then this is an example of what you could use a trigger for. I think this one almost all teams use. You have your controller object here. This one's called Xbox Controller 1. We have our trigger. So this one is built in for in WIP lib for you. You don't have to create it. But if you want to create your own, reference the docs. And this one is going to be your right bumper. This is, of course, a method of this class or this object here. And you have other things like left stick, right stick, up, POV down. It's just a button on your Xbox controller. And this returns a true or false value. And we're going to use that true or false. So we're going to use true. And we're going to say, hey, while true, we're going to run this command. And if you notice here, this one here, this is your subsystem. So their subsystem is typically one big class. And inside that class, we have a method, which is going to be our command. And our command is going to be that instruction to grab. And if you want to know more, as I said a million times already, read the documentation. It's the best way to learn about FRC, learn new things, subscribe to the channel, and we're going to add a little segment here. We're going to see a field trip, and you guys get to see what this looks like out in a real program. Well, here we are at our foreshadowed field trip. I felt like theory, you can learn as much of that as you want, but you won't really understand it unless you see it in a real project and real code. And I know a lot of teams refer to bots as some of their example code, which is why I decided to showcase that. If you want to look at our code more in depthly on your own, search up our GitHub up here. It will be in the link description, and let's go. This is our off-season robot this off-season is for Reefscape, and we use YAMS to program it, YAMS and YGSL. If you look to the side here, we have our main structures. We have our subsystems. We have our robot container, which is basically where we like combine all our subsystems and together to make a robot, right? Like kind of operation style. And then we have something here called subsystems. I'll talk a little bit more about that. What you typically see in other teams or in your team template, this is going to say commands instead. But our team, like I said before, every team organized their commands a little differently. And robots, we do that in our subsystems. In our subsystem folder, we have a subsystem for every main mechanism on our robot. We have our elevator, we have our intake arm, outtake arm, we have our rollers, we have our drivetrain, and then we also have our laser can. That we put that in a separate subsystem because it's a bit complicated. I'm pretty sure YAMS actually has a built-in class that you can use inside our YAMS library. I'm getting besides the point. If we look at our elevator subsystem, this has all the sensors and all the configurations of the motors, right? So here we created a new spark max. We defined our PID values in our closed loop controllers. We also added a follower motor in our subsystem. This is where we're putting all the details, describing what our subsystem has. In here we have our configuration saying that, hey, we're going to start at this height. There's a minimum height, a maximum height. This is all part of your subsystem. And in here, we actually don't have anything in our subsystem, but you can I know another subsystem like our swerve system, we have our limelight in here or other features. Here you have your periodic. This is or periodic and other stuff. This is gonna run every 20 something milliseconds. And if you want something that will always happen while you're running the robot, you can. This is going to be our telemetry. So this is going to always be outputting data about our robot when the robot's on. So we will always know what position it is at, how much voltage, etc. We also, here we have is going to be our trigger. This is a trigger, we haven't used it, but basically it is a true or false of has it reached its height or not, at height. And we use the is near, and it's as if it's near the target height with a tolerance of 0.1 or 0.5, I forgot what number that is, it's going to trigger this as true. You can put any Boolean in here, so you can replace all of this with just the word true if you want, and it will always return true. And then we have here, the Boolean that would actually put. So we have another Boolean here. Let's see, where's our first command? Here's a command. Since we're using YAMS, we don't have I commented out this end statement, but if we go to, let's say, our swerve subsystem, and let's see if there's a good example of a command that ends. Here's a command here, drive field oriented. It runs this, and this itself is not a command, but when we put it inside our run function, it returns as a command if that sounds confusing, pretend this says the word double or something, and then run this run here kind of converts that into that same data type. In this case, this is a command. This turns it into a command. We have our set path planner, and let's see. Oh, here. Actually, no, that's a defer. Let's see. Oh, here it is. Stop driving command. Actually, no, that was a bad one. Yeah, but look here. If you can't fit your command into one fancy return statement, you don't have to. As you can see here, we have a bunch of return methods here. Oh, here it is. So this is our drive to post command. If you want to use it, go ahead, copy, paste. All of our code is open source. And here we have our return statement that runs our swerve drive. So this is like our command. And then as soon as this command ends right here, we're going to run our returns, we're going to stop it, right? And it's going to stop when it reaches its final pose. And actually, I missed this final part. And after all of that ended, right? So once it hit its target pose, it's going to finally do stop driving. Finally do is one of those other it's like another method you can use on the command class, and it just does it after the command ends. And then we have, if we go to our robot container subsystems, think of your robot container as, well, a container that has all your robot mechanisms. Everything that combines your robot together is going to be in here. So we have our imports, where we imported all of our classes, all of our subsystems. And then we have some swerve stuff. You can go to our YGSL tutorial. I will tell you that. And in here, this is important. We basically declared all of our, or we created, we created objects of our class, or our classes here. If you don't know the basics of Java, basically in here we have a class that we declared, and we can basically use all the information in that class if we have, on all the methods and all the commands, if we have a object of it. So we created a new object called these, and then we created their new object of that. These are our systems, and they take parameters because they have constructors, and they would use these values into our class. And then we have some buttons here. So when the robot's in simulator, we have our controller. We have, this is a trigger, so it's button 1, button 2. If you're doing this in real life, you have right button, left button. And then when that's true, it's going to do our loading systems. It's going to run our elevator commands. And this one here is a parallel command along with. And then you might notice these systems here. If you're wondering about this is Bronkbot's way of organizing our commands, and we have we have our commands inside our subsystems, but to run more complex tasks, what we do is we have our loading system, and this combines a bunch of commands together. For example, we have Coral load. This runs the intake command, or the intake. It sets the intake arm down to the ground, and then along with, so this is a parallel command, it spins our intake rollers. So this uses two different subsystems, and the big thing you have to understand is that you can't have the same subsystem as a parallel command. So I can't, in this here, I can't say m underscore intake, and then let's say set pass, I don't know, set pass angle. That wouldn't work. You would get a big old fat error message, or I think it might even crash your program, because you cannot have your subsystems just two of the same subsystem. Oh my god, two of the same subsystem running at the same time. That's not possible. That's like telling your left arm to move up and then move down at the same second. Yeah. And that's about it. I guess I can also cover the robot class. Although this you would do this as like a time-based robot, right? Time-based robot, you would write everything in this class, from your autonomous to your teleop, and I just showed you all these subsystems, all these systems, and not to even mention like classes like constants where we put all of our main numbers in, so it's all in one place. Imagine all of that in just one big file. That's the true benefit of command-based programming. It's all about organization, and if you're able to organize your robot to run more efficiently, you will be able to do so much more with your robot. Not to saying that teams that do time-based robot are bad. It's just command-based programming will save you a whole lifetime of agony. And that would conclude today's tutorial. I hope you learned something new today, whether it's about commands, subsystems, command composition, or even triggers. This video is running a bit longer than I'd like, so I'm gonna end it here. Thank you for watching the video. Subscribe, follow for more tutorials relating to our new libraries, Swerve, mechanisms, and you can maybe program a pretty advanced robot like this. Have a good day and happy yassing. I used to say happy swerving, but we're not YGSL anymore. Bye.